noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to this explainer. Today, we're diving into the ultimate blueprint for reverse engineering the universe. We're going to journey all the way from the macroscopic world that we can actually touch, right down into the quantum foundations of reality. It is a fascinating look at the rules that govern, well, literally everything around us.
Now, before we really get going, I want you to consider something. What actually prevents the atoms in your body from instantly blowing apart? Think about it. Deep inside every atom is a nucleus packed with positively charged protons. By the standard laws of electromagnetism, they should repel each other with immense force. Yet here you are, holding perfectly together. Why? Well, the answer lies in the residual strong interaction. It's a force so incredibly powerful it completely overpowers that repulsion, but only at insanely microscopic distances.
Okay, let's dive right into this. Here is our 5-step cosmic toolkit for today. We're going to cover properties of the nucleus, modeling nuclear structure, radioactivity and decay, nuclear reactions and power, and finally, accelerators and particle physics.
Starting things off with Section 1, Properties of the Nucleus. So, to really understand the nucleus, we have to look at its fundamental building blocks, protons and neutrons, which we collectively call nucleons. But how do we measure something so incredibly tiny? Well, by firing high-energy electrons at the nucleus and watching how they scatter, physicists found that inside the nucleus, the density is remarkably consistent. It sits right around 0.17 nucleons per cubic femtometer. What this proves is that nuclear matter actually behaves a whole lot like a practically incompressible drop of liquid. Whether you're looking at a medium nucleus or a massive heavy one, that core density stays exactly the same.
Now, what's really interesting about this slide is how physicists calculate that binding energy without getting completely bogged down in the dense math. They use the semi-empirical mass formula, which breaks it down into 5 very practical terms. It's like a giant puzzle. You have the volume energy from short-range attraction. Then you subtract the surface energy, since the nucleons on the outside have fewer neighbors to cling to. Next, you subtract the Coulomb energy, because of that proton repulsion we talked about earlier. Then there's the asymmetry energy, dictated by quantum exclusion rules. And finally, you add a pairing term, simply because nucleons naturally prefer to pair up. It beautifully bridges classical liquid drop physics with hard quantum rules.
And, speaking of that short-range force, we absolutely have to talk about Hideki Yukawa. Back in 1935, he came up with this wild theory that nucleons stick together by essentially tossing subatomic particles back and forth, specifically massive quanta called pions. And here's the amazing part. By simply looking at the known range of the nuclear force, he mathematically predicted the exact mass of the pion. Fast forward a few years, and experiments discovered the charged pion exactly where he predicted it would be. Just brilliant.
Moving right along to Section 2, Modeling Nuclear Structure. So how exactly do we model something we can't even directly see? We use 2 massive conceptual metaphors that give us a really fascinating dual approach. On one side, you have the liquid drop model. This treats the nucleus as an incompressible fluid with surface tension. And it's fantastic for explaining macroscopic bulk properties, like why heavy nuclei become unstable and undergo spontaneous fission. But it totally fails at the quantum level. To explain that, we need the single particle shell model, which treats nucleons as moving independently within a central potential well.
This leads us to something super cool, magic numbers. Experimentalists noticed that nuclei with specific numbers of protons or neutrons, like 2, 8, 28, or 50, were exceptionally stable. The shell model explains this beautifully through something called spin-orbit coupling. Essentially, when the direction a nucleon spins happens to align with its orbit, it settles into a lower, much more stable energy state. This creates these massive, magic energy gaps between quantum shells.
We can also predict a nucleus's magnetic properties using theoretical boundary curves called Schmidt lines. But here's the kicker. Real measurements almost always fall somewhere between these bounds, not exactly on them. This hints at a really chaotic inner life of interacting particles. It shows us that the nucleus isn't just a simple, static shell. It's a deeply complex, shifting system.
All right, on to section 3, radioactivity and decay.
So what happens when this whole system gets unbalanced? When nuclei have an unstable mix of protons and neutrons, they seek stability by spontaneously shedding energy or mass. And they do this in 3 primary ways. First up is alpha decay, where a heavy nucleus spits out a helium nucleus. Think of the alpha particle trapped behind a massive energy barrier. Instead of climbing over it, it uses quantum tunneling to literally walk straight through the mountain. Second is beta decay. This is driven by weak interactions where a proton simply transforms into a neutron or vice versa. And finally, gamma decay, where an excited nucleus drops to a lower energy state by emitting a high-energy photon, very similar to an electron in an atom dropping down a shell.
Now, why does this abstract quantum decay actually matter to us? Well, think about radiocarbon dating. Cosmic rays are constantly producing carbon-14 in our atmosphere, which living things breathe in and eat. But when an organism dies, it stops taking in carbon-14. That isotope then slowly decays with a very precise half-life of 5,730 years. By measuring what's left, we can accurately determine the biological age of ancient fossils and historical artifacts. It brings the quantum world right into our daily history.
That scales us up beautifully to section 4, nuclear reactions and power. We're not just passively watching atoms decay anymore, we're actively harnessing them. A real game changer here is Niels Bohr's compound nucleus model, which splits nuclear reactions into 2 distinct steps. First, an incident particle hits a target nucleus and gets completely absorbed, rapidly distributing its energy across all the nucleons. Then, in the second step, the nucleus decays. What is completely mind-blowing about this is that the decay is entirely independent of how the compound nucleus was formed. The nucleus essentially forgets its own history and just decays based solely on its current state. When these reactions happen, we calculate the reaction Q value to track the energy shift. So what's the so what here? The crucial point is this. If the final products weigh even slightly less than the starting ingredients, that missing mass doesn't just vanish. It is converted entirely into kinetic energy. This exact trick, turning missing mass into pure, raw energy, is literally what powers the fusion in our sun and the fission inside our nuclear power plants. To actually harness that energy in a nuclear reactor, we have to control the effective neutron multiplication factor, which we call K-effective. If K-effective is less than 1, the reaction is subcritical and just dies out. If it is exactly 1, it's critical and totally stable, giving us steady power. But if it's greater than 1, it's supercritical, and the energy rapidly grows. To safely control these reactor kinetics, engineers use materials called moderators to slow down incredibly fast fission neutrons to thermal speeds.
Let's head into our final frontier, section 5, accelerators and particle physics. To really uncover the baseline rules of reality, we literally have to smash particles together at unimaginable speeds to forcibly bypass the Coulomb barrier. And to do this, physicists use an incredible arsenal of massive machines. You have electrostatic accelerators that use massive voltage drops. You've got LINACs pushing particles down linear tubes using radio frequencies. There are cyclotrons using magnetic fields to spin particles in a spiral. And for the absolute highest relativistic speeds, we use synchrotrons, keeping particles in a perfect massive ring. Smash these beams head on, and you unlock enough center of mass energy to create brand new particles out of thin air. And what have these massive colliders actually revealed? The standard model of our universe, which operates on just 4 fundamental forces. The strong force is mediated by gluons with a tiny range. The electromagnetic force is mediated by massless photons with an infinite range. The weak force is handled by heavy W and Z bosons over an extraordinarily short range. And gravity, which is currently theoretical at the quantum level, is thought to be mediated by the graviton.
Digging a little deeper into that strong force, colliders proved that protons and neutrons aren't actually fundamental. They're made of even smaller pieces called quarks. But quarks presented a mathematical puzzle. Sometimes 3 identical quarks combine, which completely breaks quantum rules, like the Pauli exclusion principle. To fix this, physicists realized quarks must carry a brand new property called color charge, red, green, or blue. This ensures no 2 quarks in a system are ever perfectly identical, keeping the math and a reality perfectly intact. Now, these subatomic rules are governed by discrete symmetries: parity, which inverts space like a mirror; charge conjugation, which swaps particles for antimatter; and time reversal, which runs the clock backward. According to the CPT theorem, if you apply all 3 simultaneously, the universe's physics remains perfectly unchanged. But here is a truly wild twist. While the strong and electromagnetic forces play nice and respect these symmetries, the weak force actively violates them. It completely ignores parity and charge conjugation. It is a wildly left-handed, rule-breaking force. Which brings up a fascinating question. Where do forces like light actually come from? In quantum physics, scientists didn't just guess that the photon existed. They found that if they took the foundational mathematical equation for an electron, the math would literally break unless they invented a new field to balance it out. That mathematically required field is the photon. Light isn't just some arbitrary feature of our reality. The universe literally demands it to keep the math balanced. How cool is that?
So that leaves us with a pretty profound mystery to wrap up on. Because that rule-breaking weak force violates charge and parity symmetry, the universe must also inherently violate time reversal symmetry, just to keep the overall physics balanced. That means the universe is fundamentally asymmetrical in time. So if these are the baseline rules of reality, what undiscovered physics lies just beyond the standard model to explain this imbalance? Thank you so much for joining this explainer, and keep questioning the universe around you.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.